Tonight, we're going to explore our nearest stellar neighbor, Alpha Centauri. If you launched a spacecraft today, traveling at the fastest speed humans have ever achieved, faster than any probe we've ever built, faster than anything we've sent into space in the entire history of spaceflight, that spacecraft would arrive at Alpha Centauri in about 6,900 years. Think about that. The ancient Egyptians built the pyramids about 4,500 years ago. If they had launched a spacecraft then, at our fastest possible speed, it still wouldn't have arrived yet. It would still be traveling through the empty darkness of space, with another 2,400 years to go. And here's what makes this truly staggering. Alpha Centauri isn't some distant, unreachable point across the galaxy. It's our closest neighbor, the nearest star system to Earth, the absolute closest possible destination beyond our sun, and yet it might as well be on the other side of the universe, for all our ability to reach it. By the end of tonight, you're going to understand exactly why even this nearest star reveals something profound and unsettling about the true scale of the cosmos we inhabit. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the southern night sky, from anywhere south of about 40 degrees north latitude, you can see Alpha Centauri with your naked eye. It appears as a single bright point of light, one of the brightest stars visible from Earth. To the casual observer, it looks like just another star, but it's not. Alpha Centauri isn't a single star at all. It's a triple star system. 3 stars gravitationally bound together, dancing around their common center of mass in an intricate cosmic ballet that's been going on for billions of years. 2 of these stars, Alpha Centauri A and Alpha Centauri B, are remarkably similar to our Sun. They're both what astronomers call main sequence stars, fusing hydrogen into helium in their cores, generating the energy that makes them shine. Alpha Centauri A is slightly larger and more massive than our Sun. It has about 110% of the Sun's mass and about 123% of its diameter. If you were standing on a planet orbiting Alpha Centauri A, the star would look very much like our Sun, perhaps a bit brighter and yellower, but unmistakably sun-like. You could imagine life arising on a planet around Alpha Centauri A, in much the same way it did on Earth. The star provides the right kind of light, the right kind of energy, the right kind of stability. Alpha Centauri B is slightly smaller, with about 90% of the Sun's mass and about 86% of its diameter. It's a bit dimmer and slightly more orange than our Sun, but still very much the same kind of star. These 2 stars orbit each other in a complex dance. They're separated by an average distance of about 23 astronomical units. An astronomical unit is the average distance between Earth and the Sun, about 93 million miles. So Alpha Centauri A and B are about 23 times farther apart than Earth is from the Sun. That might sound like a lot, and it is by terrestrial standards. But remember, our solar system extends far beyond Earth. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. So the distance between Alpha Centauri A and B is less than the distance from our Sun to Neptune. They're close together for stars. Their orbit around each other takes about 79.9 years to complete. This means that from the perspective of a planet orbiting one of these stars, you'd see the other star move slowly across the sky over decades. Sometimes it would be relatively close, appearing as a brilliant sun-like star dominating the sky. Other times it would be farther away, still bright but less overwhelming. The night sky on a planet in the Alpha Centauri system would be spectacular in ways that are hard for us to imagine. Picture standing on a world orbiting Alpha Centauri A. During the day, Your sun, Alpha Centauri A, would look much like our sun does from Earth. But when night fell and the stars came out, you'd see Alpha Centauri B shining in the darkness. Not as a point of light like we see stars from Earth, but as a tiny disk. Depending on where Alpha Centauri B was in its orbit, it might be as bright as a full moon or brighter. It would cast shadows. You'd be able to read by its light. A planet in this system would never experience true darkness the way Earth does. There would always be significant light from the companion star illuminating the night. And then there's Proxima Centauri. Proxima is the third star in the system and the one that's technically closest to us. It's a small red dwarf, dramatically different from the two larger stars. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars, but they're all so dim that not a single one is visible to the naked eye from Earth. Proxima Centauri is only about 12% of the Sun's mass and about 14% of its diameter. It's tiny by stellar standards. If you placed Proxima next to our Sun, it would look like a small ball next to a large beach ball. The difference in size is dramatic, and the difference in brightness is even more dramatic. Proxima Centauri puts out only about 0.17% as much light as the Sun. It's dim, cool, and red. Proxima orbits the Alpha Centauri A and B pair at an enormous distance. Its orbit is still somewhat uncertain because we've only been observing these stars for a relatively short time, but best estimates suggest Proxima is about 13,000 astronomical units away from the main pair. That's about 0.21 light-years. To put that in perspective, that's about 1/20th of the distance from our Sun to the next nearest star. Proxima's orbit around Alpha Centauri A and B probably takes about 550,000 years to complete. This is a loosely bound system. Proxima is so far from the other two stars that its gravitational connection to them is relatively weak. Some astronomers have questioned whether Proxima is actually gravitationally bound to Alpha Centauri A and B at all, or whether it might just be passing through the neighborhood. But current measurements of its velocity suggest it is bound, moving in a very long, very slow orbit around the main pair. From a planet orbiting Alpha Centauri A or B, Proxima would be invisible to the naked eye. It's too dim and too far away. You'd need a telescope to see it. It would just be one faint red star among thousands of other faint stars in the night sky, unremarkable except for the fact that it happens to be part of your star system. But from Proxima's perspective, Alpha Centauri A and B would be spectacular. They'd appear as two very bright stars close together in the sky, far brighter than any other stars, dominating the night. The Alpha Centauri system formed about 4.85 billion years ago, roughly the same time as our solar system. This isn't a coincidence. The stars in our region of the galaxy all formed from the same giant molecular cloud, a vast collection of gas and dust that collapsed under its own gravity. Different regions of the cloud collapsed at slightly different times, forming different stars. Our Sun formed from one collapsing region. Alpha Centauri formed from another. We're siblings in a sense, born from the same cosmic material at roughly the same time. The process of star formation is violent and chaotic. A cloud of gas and dust collapses, becoming denser and hotter. As the cloud collapses, it fragments into smaller pieces. Each piece continues collapsing, eventually forming a protostar. The protostar continues gathering material from the surrounding cloud, growing larger and denser. Eventually, the core becomes hot enough for nuclear fusion to begin. Hydrogen nuclei start fusing into helium, releasing enormous amounts of energy. This energy creates outward pressure that balances the inward pull of gravity. The star reaches equilibrium and settles onto the main sequence, where it will spend most of its life. For Alpha Centauri A and B, this process created two stars that happened to be close enough to each other that they became gravitationally bound. Instead of drifting apart, they began orbiting their common center of mass. This binary formation is common. When a gas cloud collapses, it often fragments into multiple pieces that end up orbiting each other. Single stars like our Sun are actually somewhat unusual. Most stars are born in multiples. Proxima Centauri's origin is less certain. It might have formed at the same time as Alpha Centauri A and B, part of the same collapsing cloud, or it might have formed separately and been captured by the gravity of the other two stars later. Given its enormous distance from the main pair, 13,000 astronomical units, it's possible that Proxima formed independently and just happened to pass close enough to Alpha Centauri A and B to be captured into orbit. Computer simulations of star formation suggest that capture events like this are rare but possible. If two stars pass close to each other and their velocities are just right, they can become gravitationally bound. The captured star settles into a wide orbit around the other star or stars. This might be what happened with Proxima. Or Proxima might have been born alongside Alpha Centauri A and B, farther out in the gas cloud, and simply ended up in a very wide orbit. We can't know for certain from current observations. What we do know is that the system has been stable for billions of years. The three stars have been orbiting each other in their current configuration for most of the history of the solar system. They were there when Earth formed. They were there when life first emerged on Earth. They were there during the age of the dinosaurs. They've been our nearest stellar neighbors for as long as our planet has existed. And they'll remain our nearest neighbors for millions of years into the future. The Alpha Centauri system won't stay in its current position forever. All stars in the galaxy are in motion, orbiting the galactic center. Our Sun takes about 225 million years to complete one orbit around the center of the Milky Way. Alpha Centauri has a slightly different orbit. It's moving through space at a different velocity than our Sun. Currently, the system is about 4.37 light-years away and getting closer. Alpha Centauri is approaching us at about 22,300 miles per hour. That sounds fast, and it is by terrestrial standards, but it's slow compared to the vast distance between us. At this rate, Alpha Centauri will reach its closest approach to our Sun in about 27,600 years. At that point, it will be about 3.26 light-years away, still incomprehensibly distant, still multiple trillions of miles, but closer than it is now. After reaching that closest point, Alpha Centauri will begin moving away from us. The distance will increase again. In about 1 million years, Alpha Centauri will be significantly farther away than it is now. Eventually, it won't be our nearest neighbor anymore. Some other star will take that position. This is the nature of stellar motion. Stars drift through the galaxy, their positions relative to each other constantly changing. The constellations we see in the night sky looked different to the dinosaurs and will look different to whatever creatures inhabit Earth millions of years from now. The familiar patterns are temporary, artifacts of our particular moment in time, but for now, for the entire span of human history and for thousands of years into the future, Alpha Centauri will remain our closest stellar neighbor. The first star beyond our Sun, the most accessible, if still impossibly distant, destination for any future interstellar mission. Now, Proxima Centauri is particularly interesting because it has planets. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet orbiting in the star's habitable zone. The habitable zone is the region around a star where liquid water could exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. The habitable zone is the Goldilocks region, where conditions might be just right for life as we know it. Proxima Centauri b is about 1.3 times Earth's mass and orbits its star every 11.2 days. 11 days. That seems impossibly short for a year. But remember, Proxima Centauri is a small, cool star. Its habitable zone is much closer to the star than Earth is to the Sun. Proxima b orbits at only about 0.0485 astronomical units from its star. That's about 7,250,000 miles. For comparison, Mercury, the innermost planet in our solar system, orbits at about 0.39 astronomical units from the Sun, about 8 times farther than Proxima b orbits from its star. Proxima b is close to its star, but because Proxima Centauri is so dim and cool, that close orbit might put the planet in the habitable zone. The surface temperature could potentially allow liquid water to exist. However, there are problems. Proxima Centauri is a flare star. It regularly produces powerful flares, sudden releases of energy that temporarily increase the star's brightness. These flares emit intense radiation, including X-rays and ultraviolet light. A planet as close as Proxima b would be bathed in this radiation regularly. Over time, these flares could strip away the planet's atmosphere, evaporate its water, and sterilize the surface. Life might struggle to survive in such an environment. Additionally, Proxima b is likely tidally locked to its star. This means the same side of the planet always faces the star, just like the same side of the Moon always faces Earth. One hemisphere would be in perpetual daylight, the other in perpetual darkness. This creates extreme temperature differences. The day side might be hot enough to boil water, while the night side might be cold enough to freeze everything solid. Any liquid water would likely be confined to a narrow ring around the terminator, the boundary between day and night. Winds would constantly blow from the hot side to the cold side, creating permanent hurricane-force storms. It's a hostile environment, very different from Earth. Whether life could arise and survive in such conditions is an open question. We simply don't know. Earth's life is remarkably resilient. We've found bacteria living in boiling hot springs, in frozen Antarctic ice, miles underground, in highly acidic environments, in environments with extreme radiation. Life adapts to whatever conditions exist, as long as there's liquid water and some source of energy. Proxima b might have liquid water. If it has a thick enough atmosphere to distribute heat from the day side to the night side, temperatures across the planet might be moderate enough for liquid water to exist on much of the surface. Or liquid water might be confined to underground aquifers, protected from the radiation and temperature extremes at the surface. Or the planet might be entirely covered in a global ocean, with life potentially existing in those waters. We've also learned that tidally locked planets might not be as hostile to life as we once thought. Recent climate models suggest that even with one side always facing the star, atmospheric circulation could distribute heat relatively evenly. The day side wouldn't be as hot as expected, and the night side wouldn't be as cold. A band of moderate temperatures might exist all around the planet at certain latitudes. Tidally locked planets might actually be more common in the habitable zones of red dwarfs than planets with day-night cycles like Earth. Red dwarfs are so dim that their habitable zones are very close to the star. Planets that close experience strong tidal forces that tend to lock their rotation. So if life exists anywhere in the galaxy around red dwarfs, and red dwarfs are the most common type of star, then tidally locked planets might be the most common type of habitable world. Earth, with its day-night cycle and moderate climate, might actually be the unusual case. The radiation from Proxima's flares is still a serious problem, though even if the planet has a thick atmosphere and liquid water, The intense X-ray and ultraviolet radiation from flares could make the surface uninhabitable. Life, if it exists, might need to shelter underground or underwater, emerging only during periods between flares. Or life might have evolved radiation-resistant biochemistry, able to repair DNA damage quickly. Or there might be no life at all. The planet might be a sterile rock, too close to its violent star to support any form of biology. We won't know until we observe the planet more directly. Detecting biosignatures, chemical signs of life in the planet's atmosphere, would require careful observations with next-generation telescopes. We'd look for gases like oxygen, methane, or more exotic compounds that are produced by living organisms and wouldn't exist in large quantities on a lifeless planet. Finding such gases would be strong evidence for life, though not definitive proof. Definitive proof would require much more detailed observations or, ideally, an actual mission to the planet. Imagine landing on Proxima Centauri b. Your spacecraft descends through a thick atmosphere, perhaps similar in composition to Earth's, perhaps very different. The sky might be red from the light of Proxima Centauri, the star shining small and dim compared to our Sun, but still bright enough to see clearly. The landscape below might be rocky, barren, devoid of obvious life, or it might surprise you. Perhaps there are signs of liquid water, ancient riverbeds, or currently flowing streams. Perhaps there are organic compounds, chemical precursors to life, coating the rocks. Perhaps there are actual living organisms, microbial mats clinging to wet surfaces, surviving in the harsh environment. Or perhaps the surface is entirely dead, sterilized by radiation, but beneath the ground, in caves or aquifers, life thrives in the darkness. This is all speculation, of course. We don't know what Proxima b is actually like. All we know for certain is that it exists, that it's roughly Earth's mass, and that it orbits in what might be the habitable zone. Everything else, the atmosphere, the surface conditions, the presence or absence of water and life, remains unknown. But the very fact that Proxima b exists, that our nearest stellar neighbor has a planet in the habitable zone, is significant. It suggests that habitable worlds might be common in the galaxy. If the nearest star has one, perhaps most stars do. And if most stars have habitable worlds, then the chances that life exists elsewhere in the galaxy increase dramatically. We might not be alone. There might be other worlds out there, orbiting other stars, where life has emerged and evolved, perhaps even developed intelligence and technology. Proxima b might be one of those worlds. Or it might not. But either way, its existence tells us something important about the universe we live in. Planets are common. Habitable worlds might be common. And the search for life beyond Earth has a clear starting point. Our nearest neighbor, 4.37 light-years away. There's also Proxima Centauri d, discovered in 2022, which orbits even closer to the star, and Proxima Centauri c, a more massive planet, farther out. The Alpha Centauri system is more complex than we initially thought, with multiple worlds orbiting our nearest stellar neighbor. But here's the thing that brings us to the heart of tonight's story. Despite being our closest neighbor, despite being right next door in cosmic terms, Alpha Centauri is incomprehensibly far away. The system is about 4.37 light-years from Earth. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. In 1 year, light travels about 5.88 trillion miles. So 4.37 light-years is about 25.69 trillion miles. Let's try to understand what this distance actually means. If you got in a car and drove toward Alpha Centauri at highway speed, say 65 miles per hour, driving continuously without stopping, how long would it take? The answer is about 45 million years. That's longer than humans have existed as a species. Homo sapiens emerged about 300,000 years ago. You could have started driving when the first humans appeared, driven continuously at highway speed for 300,000 years, and you'd only be about 0.67% of the way there. Let's try a faster vehicle. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached a top speed of about 119 miles per second when it came close to the Sun. That's about 430,000 miles per hour, unimaginably fast by any human standard. At that speed, you could circle Earth's equator in less than an hour. You could reach the Moon in about 33 minutes. You could reach the Sun in about 36 days. At that speed, how long would it take to reach Alpha Centauri? About 6,900 years. That's longer than all of recorded human history. Writing was invented about 5,000 years ago in ancient Mesopotamia. If you'd launched a spacecraft at Parker Solar Probe speeds when humans first learned to write, traveled continuously at the fastest speed any human-made object has ever achieved, that spacecraft would still be traveling today, still about 1,900 years away from Alpha Centauri. The pyramids of Giza were built about 4,500 years ago. A spacecraft launched then would still have about 2,400 years to go. The Roman Empire fell in 476 CE, about 1,548 years ago. A spacecraft launched then would still have about 5,352 years to go. Even Voyager 1, launched in 1977, and currently the most distant human-made object, traveling at about 38,000 miles per hour, would need about 73,000 years to reach Alpha Centauri. And it's not even aimed in that direction. These aren't just big numbers. They represent a fundamental barrier. The distances between stars are so vast that with any technology we currently have or can even imagine developing in the near future, interstellar travel is effectively impossible within a human lifetime. Let's scale this down to make it more tangible. Imagine our solar system shrunk so that the distance from the Sun to Neptune, the outermost planet, is 1 inch. On this scale, the Sun would be far too small to see, smaller than a grain of sand. Earth would be invisible, far smaller than any microscopic organism. The entire solar system, everything that orbits our Sun out to Neptune, fits in 1 inch. On this same scale, how far away would Alpha Centauri be? About 787 feet. That's more than the length of 2.5 football fields. The vast majority of that space is nothing. Just empty void. If you tried to make a scale model of our cosmic neighborhood that fits in a normal room, you couldn't do it. The distances are too large. You could fit the entire solar system on a tabletop, but you'd need multiple football fields to include Alpha Centauri. Let's try another analogy. If the Sun were the size of a basketball, Earth would be a tiny bead about 2 millimeters across, sitting about 85 feet away. That's about the length of 2 school buses parked end to end. On this same scale, Alpha Centauri would be about 5,400 miles away. That's roughly the distance from New York to London. You could place your basketball sun in New York, and Alpha Centauri A would be in London. And in all that space between, there would be nothing. Just empty void. This is what space is actually like. Tiny islands of matter separated by incomprehensible distances of nothing. The distances between stars are so enormous compared to the sizes of stars and planets that if you made a scale model showing both the sizes and the distances accurately, the stars would be invisible. You couldn't see them. They'd be too small. This is why diagrams of the solar system and the galaxy are always misleading. To show the planets, they have to make the planets vastly larger than they should be in proportion to the distances. Otherwise, the planets would be invisible dots, and the diagram would be useless. The same is true for diagrams of the galaxy. Stars have to be drawn much larger than they really are in proportion to the distances between them, or else you just see nothing. Now, you might be thinking, surely with future technology, we could develop faster spacecraft. We could build something that travels a significant fraction of the speed of light, that would make the trip possible within a human lifetime. This is true in principle. If you could build a spacecraft that traveled at 10% of the speed of light, about 18,600 miles per second, you could reach Alpha Centauri in about 43.7 years. Still a lifetime, but possible. Launch the mission when you're 20 years old, and you might live to see it arrive when you're in your 60s. At 20% of light speed, the trip would take about 21.85 years. Launch it when you're 30, and it arrives when you're in your early 50s. But here's the problem. We have no idea how to build a spacecraft that travels at even a small fraction of the speed of light. The Parker Solar Probe, our fastest spacecraft, reaches about 0.064% of light speed at its maximum velocity. To get to 10% of light speed, we'd need to build something about 156 times faster than our fastest spacecraft. And spacecraft speed isn't like car speed, where you just need a bigger engine. The energy requirements scale dramatically. Kinetic energy, the energy of motion, increases with the square of velocity. Double the speed, and you need 4 times the energy. Triple the speed, and you need 9 times the energy. To reach 10% of light speed would require energy scales that dwarf anything we currently use. Let's put this in perspective. The Parker Solar Probe has a mass of about 685 kilograms. To accelerate that mass to 10% of the speed of light, you'd need about 2.7 times 10 to the power of 17 joules of energy. That's about 64 megatons of TNT equivalent. For reference, the largest nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, released about 50 megatons of energy. You'd need more than the largest nuclear explosion in history just to accelerate a small probe to 10% of light speed. And that assumes perfect efficiency, which is physically impossible. Real propulsion systems lose energy as heat, exhaust, and other inefficiencies. You'd probably need several times that much energy in practice. Where would that energy come from? Chemical rockets are completely inadequate. The best chemical rockets can achieve speeds of a few miles per second. To reach tens of thousands of miles per second, you need something fundamentally different. Nuclear propulsion might help. Nuclear fission or fusion could provide energy densities far higher than chemical reactions. But even nuclear propulsion faces severe limitations. You'd need to carry fuel, and fuel has mass, and accelerating that mass requires even more fuel. This is the tyranny of the rocket equation. The more fuel you carry, the more mass you have to accelerate, which requires more fuel, which adds more mass, and so on. For interstellar journeys, the rocket equation becomes brutal. There's been one serious proposal for a spacecraft that might reach a significant fraction of light speed within the bounds of known physics. It's called Breakthrough Starshot, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. The concept is elegant. Instead of carrying fuel, you use light to push the spacecraft. You build an extremely lightweight spacecraft, essentially a computer chip with a camera attached to an ultra-thin reflective sail, weighing perhaps a gram. Then you point massive laser arrays at it from Earth. The laser light pushes on the sail, and because the spacecraft is so incredibly light, it can be accelerated to tremendous speeds. The proposal calls for accelerating the spacecraft to about 20% of light speed. At that speed, it could reach Alpha Centauri in about 21.85 years. Add another 4.37 years for signals to travel back at light speed, and you could potentially get data from Alpha Centauri in about 26.22 years from launch. That's within a human lifetime. You could launch a mission when you're young and potentially see the results before you die. But the engineering challenges are staggering. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a laser beam a few miles wide. Building such a laser array would cost tens of billions of dollars, possibly more. Second, you need to focus that laser beam on a tiny spacecraft that's accelerating rapidly and getting farther away every second. This requires extraordinarily precise targeting and adaptive optics to compensate for atmospheric distortion. Even tiny aiming errors would cause the laser to miss the sail, and once you miss, you can't get the spacecraft back. Third, the spacecraft needs to survive acceleration. To reach 20% of light speed within a few minutes of laser acceleration, the spacecraft experiences enormous G-forces. The electronics need to be ruggedized to survive. Fourth, at 20% of light speed, even tiny particles become dangerous. A grain of dust hitting the spacecraft at this speed would release as much energy as a significant explosion. The spacecraft would need shielding, but shielding adds mass, which reduces acceleration. Fifth, communication is difficult. At Alpha Centauri, the spacecraft would be about 4.37 light-years away. A tiny spacecraft has very limited power for transmitting signals. To receive those signals on Earth, you'd need enormous radio telescopes pointed at exactly the right spot for years, waiting for the signal to arrive. Sixth, you can't slow down. A light sail pushed by lasers from Earth can accelerate on the way out, but there's no way to decelerate at the destination. The spacecraft would fly past Alpha Centauri at 20% of light speed, giving it a few hours at most to take pictures and measurements before zooming past and continuing into interstellar space forever. Despite these challenges, Breakthrough Starshot is probably the most realistic proposal we have for reaching another star system within a human lifetime using known physics. It's ambitious, expensive, and technically daunting, but it's not obviously impossible. Whether it ever gets built is another question. It would require sustained international cooperation and funding on a scale comparable to the Apollo program or larger. And even if it succeeds, it would only send a tiny probe, not humans, not a spacecraft that could land and explore, just a chip-sized camera flying past at enormous speed, taking pictures for a few hours. But even that would be extraordinary. Images of planets around Alpha Centauri, if they exist, measurements of the star's properties up close, data from another star system. It would be humanity's first step beyond the solar system, our first physical contact with the nearest stars. The question of sending humans to Alpha Centauri is even more daunting. A crewed mission faces all the same challenges as a probe mission, plus many more. Humans need life support, food, water, air, radiation shielding, and space to live. They can't be shrunk down to a gram. A crewed spacecraft would need to be massive compared to a chip-sized probe. It would need engines or sails capable of accelerating that much larger mass. And unlike a flyby probe, a crewed mission would need to slow down at the destination. Accelerating to a significant fraction of light speed is hard enough. Decelerating is equally hard and requires just as much energy. You'd need to carry fuel or have some other method to slow down, which adds even more mass. Then there's the time problem. Even at 10% of light speed, the journey would take about 43.7 years. That's a significant chunk of a human lifetime. The crew would age. They'd need to deal with the psychological challenges of being confined in a small spacecraft for decades, with no possibility of turning back or receiving help from Earth. Communication delays would make conversations with Earth impossible. At Alpha Centauri, a radio signal takes 4.37 years to reach Earth. If you sent a message home, you'd wait nearly 9 years for a response. By the time you received an answer to your question, you might have forgotten what you asked. There's also the cosmic ray problem. Outside Earth's protective magnetic field and atmosphere, astronauts are exposed to cosmic rays, high-energy particles from space that can damage DNA and increase cancer risk. On the International Space Station, astronauts are still within Earth's magnetic field, which provides some protection. In interstellar space, there's no such protection. A crewed mission to Alpha Centauri would need heavy shielding or some other method to protect the crew from radiation for decades. The radiation problem is serious and multifaceted. Cosmic rays come from multiple sources. Some originate from the sun during solar flares. Others come from supernova explosions in distant parts of the galaxy. The most energetic cosmic rays might come from outside our galaxy entirely, from active galactic nuclei or other extreme environments. These particles, mostly protons and atomic nuclei, travel at nearly the speed of light. When they hit matter, they can cause significant damage. In biological tissue, cosmic rays can break apart DNA molecules, causing mutations. A single high-energy particle can damage many cells along its path. For astronauts on short missions, the risk is manageable. A few months or even a year in space doesn't result in dangerous radiation doses, though it does increase cancer risk slightly. But for a multi-decade mission to Alpha Centauri, the cumulative radiation dose would be substantial, unless the spacecraft has significant shielding. The problem is that shielding is heavy. Water is one of the best radiation shields, and it has the advantage of being useful for other purposes, like drinking and growing food. A spacecraft could surround its crew compartment with water tanks, providing both radiation protection and a reserve of water. But water is heavy, about 62.4 pounds per cubic foot. To provide adequate shielding for a crew compartment, you'd need meters of water on all sides. That's an enormous amount of mass. And remember, every kilogram of mass you add to the spacecraft requires more energy to accelerate. The tyranny of the rocket equation strikes again. More shielding means more mass, which means more fuel, which means more mass, which means more fuel. You quickly reach a point where the spacecraft becomes impossibly massive. Other shielding materials exist, of course. Lead is dense and blocks radiation well, but it's even heavier than water. Plastics and other hydrocarbon materials are actually quite good at blocking radiation because they contain lots of hydrogen, which is effective at absorbing energetic particles. But again, you need significant thickness, and thickness means mass. Some have proposed using the spacecraft's own propellant as shielding. If you're carrying tons of fuel anyway, arrange it around the crew compartment so it provides radiation protection during the journey. As the fuel is consumed, the shielding decreases, but hopefully by the time most of the fuel is gone, you're close to your destination, and the reduced exposure time makes the higher radiation dose acceptable. This is clever, but it requires careful design to ensure the propellant tanks are positioned correctly and that consuming fuel doesn't create weak spots in the shielding. Another approach is active shielding, using magnetic or electric fields. Just like Earth's magnetic field deflects cosmic rays, a spacecraft could generate its own magnetic field to deflect particles. This is theoretically possible, but practically very difficult. You'd need powerful electromagnets or superconducting coils generating intense fields. The power requirements would be substantial, and magnetic fields only work well against charged particles. Neutrons, which make up a significant fraction of cosmic rays, aren't affected by magnetic fields at all. You'd still need some physical shielding. Despite these challenges, radiation shielding is probably solvable. It's a known problem with known solutions. Even if implementing those solutions adds mass and complexity, we know how to block radiation. We just need to build a spacecraft robust enough to carry adequate shielding while still being light enough to accelerate to high speeds. That's a tough engineering challenge, but not an impossible one. But radiation is only one of many life support challenges for a crewed interstellar mission. You also need air, water, food, and waste recycling. For a mission lasting decades, you can't simply bring supplies from Earth. There isn't enough storage space, and the mass would be prohibitive. Instead, you need closed-loop life support systems that recycle everything. The International Space Station already does this to some extent. Water is recycled from condensation, urine, and other sources, purified, and reused. The same water molecules cycle through the crew's bodies over and over. Air is also partially recycled. Carbon dioxide exhaled by the crew is filtered out and either vented to space or chemically converted back into oxygen. But the ISS isn't a perfect closed loop. It still requires regular resupply missions bringing fresh water, food, spare parts, and other necessities. An interstellar spacecraft would need to be completely self-sufficient, capable of recycling air and water with near-perfect efficiency for decades. Any leaks or inefficiencies would slowly deplete reserves until the mission failed. Food is even more challenging. The ISS receives regular shipments of freeze-dried and packaged food from Earth. An interstellar spacecraft can't do this. It would need to grow food aboard. This means hydroponic or aeroponic gardens, carefully tended plants growing under artificial light, producing edible crops. We've experimented with growing plants in space on the ISS and other spacecraft. Lettuce, wheat, tomatoes, and other crops have been successfully grown in microgravity. But scaling this up to feed a crew for decades is a massive undertaking. You'd need significant space devoted to growing food, powerful lights to provide energy for photosynthesis, careful climate control to maintain proper temperature and humidity, and constant attention from the crew to tend the plants. And you'd need variety. A crew eating nothing but lettuce and wheat for 40 years would face nutritional deficiencies and psychological burnout from monotony. You'd want to grow multiple crops, providing a varied diet that keeps the crew healthy and mentally engaged. Some have proposed bringing along insects or fish as protein sources, creating a more complete, closed ecosystem. But this adds complexity. Every additional organism requires its own life support, its own food source, its own waste management. And there's the risk that something in the ecosystem could fail, causing a cascade of problems. Perhaps the simplest approach is to bring frozen or preserved food for protein and other nutritionally dense foods, while growing only a portion of the diet aboard. This reduces the load on the spacecraft's agricultural systems while ensuring the crew has access to complete nutrition. But it requires careful planning and significant storage. Then there's the psychological aspect. Humans are social creatures, evolved to live in communities with hundreds or thousands of other people. Confining a small group, perhaps 5 to 10 people, in a small spacecraft for decades would create intense psychological pressures. The crew would see the same faces every day for years. Every personality quirk, every annoying habit, every disagreement would be magnified by the confined space and long duration. There's no escape, no ability to take a break and go somewhere else. Careful crew selection would be critical. You'd need people who are not only technically skilled, but also psychologically resilient, capable of handling stress, isolation, and interpersonal conflict without breaking down. You'd also need to provide mental stimulation. Books, movies, games, educational materials, hobbies, anything to keep the crew's minds engaged. Virtual reality could help, creating the illusion of larger spaces or different environments. But even with these measures, the psychological toll would be immense. Studies of isolated groups in extreme environments, like Antarctic research stations or submarine crews, show that even highly trained and selected individuals struggle with isolation. Depression, anxiety, and interpersonal conflicts are common. An interstellar mission would be orders of magnitude more challenging. The crew would know that there's no possibility of rescue, no early return, no chance to see friends and family for decades. They'd watch Earth recede in the distance, becoming first a bright star, then just another point of light among millions, eventually invisible. They'd be truly alone in a way few humans have ever experienced. And communication with Earth would become increasingly difficult. At Alpha Centauri, light takes 4.37 years to travel between the spacecraft and Earth. If a crew member sends a message home, "How are you? I miss you," that message would take 4.37 years to arrive. The response would take another 4.37 years to travel back. By the time the crew member receives a response, nearly 9 years will have passed. The conversation would be meaningless. You can't have a relationship, can't maintain emotional connections, when every message takes nearly a decade for a round trip. The crew would essentially be cut off from Earth, unable to communicate in any meaningful way. They could send status updates, scientific observations, requests for advice on technical problems. But anything time-sensitive would have to be decided by the crew alone. If something goes wrong, if there's a medical emergency or a system failure, mission control on Earth can't help. By the time Earth receives the distress signal and sends back advice, the situation would have resolved one way or another, for better or worse. This is radically different from every other space mission in history. Apollo astronauts on the Moon were only a few seconds away by radio. Even a signal delay of a few seconds allows for real-time-ish conversation. ISS astronauts have essentially no delay when talking to mission control. Mars missions, the next big step in human spaceflight, would have delays of anywhere from 3 to 22 minutes each way, depending on the positions of Earth and Mars in their orbits. That's annoying but manageable. You can still ask a question and get an answer the same day, but 4.37 years each way is fundamentally different. It's not just a long delay. It's the end of meaningful real-time communication. The crew would be autonomous, making all decisions themselves, cut off from home in every practical sense. This isolation extends to scientific knowledge as well. If scientists on Earth make a breakthrough discovery that could help the mission, the crew won't learn about it for years. If the spacecraft encounters an unexpected problem that's never been seen before, Earth scientists and engineers can't help solve it in time. The crew must rely entirely on their own training, knowledge, and ingenuity. This places enormous responsibility on the crew and on the mission planners. The spacecraft must be designed with redundancy, capable of handling problems without external help. The crew must be trained extensively, prepared for as many contingencies as possible. And even then, there will inevitably be surprises, situations no one anticipated. The crew will have to figure things out on their own, millions of miles from home, with no one to call for help. All of this assumes the mission uses conventional propulsion, taking decades to reach Alpha Centauri. If we could somehow accelerate to a much higher fraction of light speed, the journey would be shorter. At 50% of light speed, the trip would take about 8.74 years. Still a long time, but at least within a single digit of years rather than decades. At 90% of light speed, about 2.9 years by the spacecraft's clock, though time dilation becomes significant at these speeds. People on Earth would age more than the crew due to relativistic effects. But achieving these speeds faces even more daunting challenges than the 10% of light speed we've been discussing. The energy requirements scale rapidly. relativistic effects become important. Collisions with interstellar particles, even tiny grains of dust, release enormous energy. At 90% of light speed, hitting a grain of dust would be like detonating a small bomb. The spacecraft would need massive shielding just to survive the journey, and slowing down becomes nearly impossible. The energy required to decelerate from 90% of light speed is just as large as the energy required to accelerate. You'd need either to carry enormous amounts of fuel, which adds mass and makes acceleration even harder, or you'd need some way to gather reaction mass during the journey, which introduces its own set of problems. Practically speaking, with any technology we can currently envision, crewed missions to Alpha Centauri are impossible. The distances are too large, the energy requirements too high, the technical challenges too numerous. This doesn't mean it will never happen. 1,000 years from now, humanity might have developed technologies we can't currently imagine. Perhaps fusion power will become practical, providing compact, efficient energy sources. Perhaps advances in materials science will create incredibly strong, lightweight materials, perfect for spacecraft construction. Perhaps breakthroughs in biology and medicine will extend human lifespans to centuries, making a 40-year journey seem less daunting. Perhaps artificial intelligence and robotics will advance to the point where we don't need to send biological humans at all. We could send AI-controlled robots capable of functioning for centuries, exploring the Alpha Centauri system and sending back detailed information. Or perhaps we'll develop some form of suspended animation or cryogenic freezing, allowing crew members to sleep through most of the journey and wake only when they arrive. Or perhaps we'll upload human consciousness into machines, transforming ourselves into digital beings who don't need life support or radiation shielding and who can survive indefinitely in space. These ideas range from speculative to science fiction, but they illustrate the point. The barriers to reaching Alpha Centauri with current technology are immense. But technology changes. What seems impossible today might be routine in the future, or it might remain impossible. We don't know. What we do know is that with the physics and engineering we understand today, sending humans to Alpha Centauri is beyond our capabilities. The distances are simply too vast. Some have proposed generation ships, massive spacecraft designed to sustain a population for multiple generations. The initial crew would launch, knowing they'd never reach the destination. Their children might not reach it either. It would be their grandchildren or great-grandchildren who'd arrive at Alpha Centauri decades or centuries after launch. This raises profound philosophical and ethical questions. Is it right to commit unborn generations to a journey they didn't choose? What kind of society would develop aboard such a ship, isolated from Earth for generations? How would you maintain the technological knowledge needed to complete the mission over such timescales? Others have proposed suspended animation or cryogenic freezing, where the crew would be put into a state of hibernation for the journey and awakened upon arrival. This remains science fiction. We don't have the technology to put humans into suspended animation safely. Every attempt to freeze and revive mammals has resulted in fatal cell damage from ice crystal formation. There are some promising leads in research on tardigrades and certain fish species that can survive freezing, but we're nowhere close to applying this to humans. Another idea is the antimatter rocket. When matter and antimatter collide, they annihilate completely, converting all their mass into energy according to Einstein's equation E equals mc squared. This is the most energetically efficient reaction possible in physics. An antimatter rocket could theoretically achieve very high speeds, potentially reaching a significant fraction of light speed. But producing antimatter is extraordinarily difficult and expensive. Antimatter exists naturally in tiny quantities, but producing it deliberately requires enormous particle accelerators. The total amount of antimatter ever produced by humanity is measured in nanograms. To fuel an antimatter rocket for an interstellar journey, you'd need kilograms or tons of antimatter. At current production rates and costs, producing even a single gram of antimatter would cost hundreds of trillions of dollars. And storing antimatter is another huge challenge. Antimatter annihilates instantly upon contact with matter, so it must be stored in magnetic or electric fields that keep it suspended away from the container walls. Any failure in the containment system would result in an explosion. These aren't just engineering problems. They're fundamental barriers that might never be fully overcome. The distances between stars might simply be too large for any biological organism to cross within its lifetime, using any technology consistent with the laws of physics, as we understand them. Some physicists have speculated about exotic solutions like wormholes or warp drives, concepts from general relativity that might, in principle, allow faster-than-light travel. But these ideas face enormous theoretical and practical problems. Wormholes, if they exist, would likely be incredibly unstable and collapse before anything could pass through. Keeping them open would require exotic matter with negative energy density, something that's never been observed and might not exist. Warp drives, as proposed by physicist Miguel Alcubierre, would involve warping space-time itself, creating a bubble of contracted space in front of the ship and expanded space behind it. The ship wouldn't move faster than light locally, but space-time itself would move, carrying the ship along. But this also requires exotic matter with negative energy density in enormous quantities, possibly more than exists in the entire observable universe. And there are causality problems. If you could travel faster than light using these methods, you could potentially travel backward in time, creating paradoxes. As far as we know, based on over a century of experiments and observations, the speed of light is an absolute barrier for anything moving through space. It's not a limit we might overcome with better technology. It's a fundamental feature of how space and time are structured. So when we talk about Alpha Centauri being 4.37 light-years away, we're not just talking about a large distance. We're talking about a journey that would take at least 4.37 years, even if you could travel at the speed of light, which is impossible for anything with mass. More realistically, with any conceivable technology, we're talking about journeys measured in decades or centuries. This is the true scale of Alpha Centauri. It's right next door, in cosmic terms, the closest possible destination beyond our solar system, and yet it might as well be unreachable. The distances involved are so vast that they challenge the very concept of exploration and travel as we understand them. But let's zoom out even further to understand just how unusual this isolation is. Alpha Centauri is our closest neighbor at 4.37 light-years. The next nearest star system is Barnard's star at 6 light-years, then Wolf 359 at 7.9 light-years, Sirius at 8.6 light-years. These are the stars in our immediate neighborhood, and they're all multiple light-years away. The average distance between stars in our region of the galaxy is about 5 light-years. We're not in an unusually crowded or unusually empty region. This is typical. Most stars in the galaxy are separated by distances of several light-years. There are denser regions near the galactic center where stars are packed more closely together. In the core of the galaxy, stars might be only a few light-months apart, but we're not there. We're in the galactic suburbs, about 26,000 light-years from the center, where the stellar density is relatively low. Globular clusters are another place where stars are packed tightly. These are ancient, spherical collections of stars orbiting the galaxy. In the cores of globular clusters, stars can be separated by only a few light weeks or even light days. If you lived on a planet in a globular cluster, your night sky would be spectacular. thousands of stars would be bright enough to cast shadows. The sky would never truly be dark. But even in these dense environments, stars don't collide. The distances are still enormous compared to the sizes of stars. Space is big, and stars are tiny. Our Sun has a diameter of about 864,000 miles. That sounds large, but it's tiny compared to interstellar distances. If you could line up suns end to end from here to Alpha Centauri, you'd need about 33 million suns. The distance between stars is about 33 million times the diameter of a star. This ratio is typical throughout the galaxy. Stars are like grains of sand, separated by miles, like atoms in a vacuum. Like fireflies on opposite sides of a continent. The galaxy is almost entirely empty space, with tiny islands of matter scattered throughout. When we look at pictures of galaxies, they appear as solid objects, glowing disks or spirals of light. But this is an illusion created by long-exposure photographs. If you could actually fly through a galaxy at high speed, you'd notice the emptiness. You could travel for years without coming anywhere near a star. The light from all those distant stars would create a glow in the sky. But most of your view would be empty blackness. The Milky Way galaxy contains between 100 billion and 400 billion stars spread across about 100,000 light-years. That's an enormous range, because it's actually quite difficult to count stars in our own galaxy. We're inside it, like trying to count trees while standing in the middle of a forest. Dust blocks our view in many directions. Dim stars are hard to detect. But even taking the high estimate of 400 billion stars, the average volume of space per star is about 33 cubic light-years. Imagine a cube 33 light-years on each side with one star somewhere inside it. Most of that cube is empty. This is the reality of our galaxy, and indeed of the entire universe. Matter is rare. Emptiness is common. The vast majority of space contains nothing at all, not even atoms. Just empty void punctuated occasionally by a wandering particle or a photon passing through. This emptiness is profound and fundamental. It's not an accident or a temporary condition. It's a consequence of how the universe evolved. After the Big Bang, matter was initially spread relatively evenly throughout space. But tiny density variations, quantum fluctuations from the earliest moments, caused some regions to have slightly more matter than others. Gravity amplified these differences. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to neighboring denser regions, becoming emptier. Over billions of years, this process created the structure we see today. Stars, planets, galaxies, clusters, and superclusters separated by vast voids. The universe self-organized into a cosmic web of filaments and walls surrounding empty regions. And within the filaments, galaxies formed. And within galaxies, stars formed. And around some stars, planets formed. And on at least one planet, life emerged. But at every scale, the dominant feature is emptiness. Most of the universe is void. Alpha Centauri represents our first step beyond that void, our first opportunity to reach across the emptiness to another island of matter. And even this first step is almost impossibly difficult. Now let's talk about what Alpha Centauri actually looks like and how we discovered what we know about it. For thousands of years, humans have looked up at Alpha Centauri without understanding what they were seeing. Ancient civilizations saw it as just another bright star in the southern sky. Different cultures gave it different names and incorporated it into their mythologies. The ancient Greeks couldn't see Alpha Centauri from most of their territory because it's too far south. But Greek astronomers working in Alexandria, Egypt, which is farther south, would have been able to see it low on the southern horizon. Ptolemy, the 2nd century Greek astronomer whose geocentric model dominated astronomy for over 1,000 years, included Alpha Centauri in his star catalogue. He listed it as part of the constellation Centaurus, the centaur, a mythological creature that's half human and half horse. Alpha Centauri marks the centaur's front foot or hoof, depending on the depiction. Arab astronomers also catalogued the star. They called it Rigil Centaurus, which means foot of the centaur in Arabic. This name is still sometimes used today. Other alternative names include Ptolemy and Bungula, though Alpha Centauri is the designation most commonly used in modern astronomy. To these ancient observers, Alpha Centauri was simply a bright star, no different in principle from hundreds of other bright stars scattered across the night sky. They had no way of knowing it was actually multiple stars, no way of knowing how far away it was, no way of knowing that it was our nearest stellar neighbor. The technology and understanding required to learn those things wouldn't exist for many centuries. The first major discovery about Alpha Centauri came in the late 1600s, when telescopes became powerful enough to reveal details invisible to the naked eye. From Earth, Alpha Centauri appears as a single star to the naked eye, but even small telescopes can resolve it into two distinct stars, Alpha Centauri A and Alpha Centauri B, orbiting each other. This was first observed in 1689 by Father Jean Richaud, a Jesuit priest working at Pondicherry Observatory in India. He wasn't looking for binary stars. He was observing a comet, tracking its position as it moved across the sky. Alpha Centauri happened to be nearby, and when Richaud pointed his telescope in that direction, he noticed something unusual. What appeared to be a single bright star to the naked eye clearly showed two distinct points of light through the telescope. This was surprising. Most stars, even when viewed through a telescope, still appear as single points of light. They're so far away that even the best telescopes can't resolve them into disks. Stars are just points. But in rare cases, when two stars happen to be very close together in the sky, and at least one of them is relatively nearby, a telescope can separate them into two distinct objects. Richaud had discovered that Alpha Centauri was actually a binary star system, two stars orbiting each other. This discovery was significant because it proved that not all stars are alone like our Sun. Many stars, perhaps most, are part of multiple star systems. Binary stars, triple stars, and even larger systems are extremely common in the galaxy. Current estimates suggest that about half of all Sun-like stars are part of binary or multiple star systems. This has profound implications for planet formation and the possibility of life. Planets in binary star systems experience more complex gravitational environments than planets orbiting single stars. Their orbits can be less stable. The presence of a second star can disrupt planet formation or throw planets out of the system entirely. But planets can still form and survive in such systems, as we've discovered around many binary stars. After Richaud's discovery, other astronomers began observing Alpha Centauri more carefully. They tracked the positions of the two stars over years and decades, measuring how they moved relative to each other. By the early 1800s, it was clear that Alpha Centauri A and B were indeed orbiting each other, locked in a gravitational dance. The orbit takes about 79.9 years to complete. This meant that to see one full orbit, you'd need to observe continuously for a human lifetime. Astronomers in the early 1800s were observing stars that had been measured decades earlier by previous generations of astronomers. They were literally watching stars move over the course of human lifetimes. But the biggest question remained unanswered. How far away was Alpha Centauri? For all of human history up to that point, we had no way of measuring the distance to any star. We could see them, catalogue them, track their positions, but we couldn't determine how far away they were. Stars could be relatively nearby or unimaginably distant. There was no way to tell. This changed in the 1830s. when astronomers developed a technique called stellar parallax. Parallax is the apparent shift in position of an object when viewed from two different locations. Hold your finger up at arm's length and look at it with one eye closed, then switch eyes. Your finger appears to jump position relative to the background. That's parallax. The same principle works for stars. As Earth orbits the Sun, our viewing position changes. We see stars from slightly different angles at different times of year. Nearby stars appear to shift position slightly relative to more distant background stars. By measuring this shift, you can calculate the star's distance using basic trigonometry. The problem is that the shifts are tiny. Even the nearest stars show parallax shifts of less than 1 arc-second. An arc-second is 1/3600th of a degree. It's the angle subtended by a coin viewed from about 2.5 miles away. Measuring such tiny angles requires extraordinary precision. In 1838, German astronomer Friedrich Wilhelm Bessel made the first successful measurement of stellar parallax. He observed 61 Cygni, a star in the constellation Cygnus, and measured a parallax of about 0.314 arc-seconds. From this, he calculated that 61 Cygni was about 11.4 light-years away. This was revolutionary. For the first time in human history, we knew the distance to a star other than the Sun. The universe was suddenly much larger than anyone had imagined. Within months of Bessel's announcement, other astronomers reported parallax measurements for other stars. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published parallax measurements for Alpha Centauri. Interestingly, Henderson had actually made his observations before Bessel, starting back in 1832. He had measured Alpha Centauri's position carefully over many months, tracking its apparent motion across the sky. But Henderson was cautious, perhaps too cautious. He saw a shift in position that looked like parallax, but he wasn't completely confident in his results. He worried about systematic errors, about whether his instruments were accurate enough, about whether he might be seeing some other effect. So he sat on his data, continuing to analyze it, hesitating to publish. When Bessel's announcement came through in early 1839, Henderson realized his own measurements were valid. He rushed to publish his results. His data was actually better than Bessel's in some ways, because Alpha Centauri is brighter and closer, making the parallax larger and easier to measure. Henderson's measurements showed that Alpha Centauri was about 4.4 light-years away, making it the nearest known star to the Sun. This is interesting from a history of science perspective. Henderson actually made the first stellar parallax measurements, but Bessel gets credit for the discovery because Bessel published first. This happens sometimes in science. The person who publishes first gets the credit, even if someone else did the work earlier. It's why scientists often rush to publish as soon as they have solid results. Speed matters. Being right is important, but being first to publish is what determines who gets remembered. Modern measurements with better instruments have refined Henderson's result. We now know Alpha Centauri is 4.37 light-years away, very close to Henderson's original measurement. The precision of his work, using 1830s technology, is remarkable. He was measuring angles smaller than anything that had been measured before, pushing the limits of what was possible with the telescopes and techniques available at the time. The discovery of Proxima Centauri came much later. In 1915, Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg, South Africa, noticed a faint red star on photographic plates that showed a large, proper motion. Proper motion is the apparent motion of a star across the sky over time due to its actual movement through space. Most stars appear fixed relative to each other because they're so far away that their motion is imperceptible. but nearby stars show measurable proper motion over decades or centuries. Innes measured Proxima's proper motion and found it was moving across the sky at about 3.85 arcseconds per year. That might not sound like much. An arcsecond is 1/3600th of a degree, but it's enormous by stellar standards. Most stars have proper motions measured in tiny fractions of an arcsecond per year. Proxima's large proper motion suggested it was relatively close to us. Innes also noticed that Proxima's motion across the sky was similar to the motion of Alpha Centauri A and B. They were all moving in the same direction at similar rates. This suggested they might be part of the same system, gravitationally bound together. Further observations confirmed this. Proxima Centauri is slightly closer to us than Alpha Centauri A and B, making it the nearest known star to the Sun. The name Proxima means nearest in Latin. For decades, Proxima Centauri was just a curiosity, a faint red dwarf that happened to be our closest neighbor but was otherwise unremarkable. It was too dim to study in detail. Most astronomical research focused on brighter, more distant objects, but in recent decades, advances in telescope technology and detection methods have allowed us to study Proxima in much greater detail. We've measured its spectrum, determining its temperature, composition, and physical properties. We've detected its flares, measuring their energy and frequency. And we've discovered its planets. The discovery of Proxima Centauri b in 2016 was a watershed moment. It proved that our nearest stellar neighbor has planets, and one of those planets orbits in the habitable zone. The possibility, however remote, that life might exist on a planet orbiting the nearest star to our Sun is tantalizing. It's almost too convenient, too perfect. The closest star happens to have a potentially habitable planet. But this might not be as much of a coincidence as it seems. Red dwarfs are the most common type of star in the galaxy, and planets appear to be common around red dwarfs. If most stars have planets, and most stars are red dwarfs, then it's not surprising that the nearest star, which happens to be a red dwarf, has planets. What we don't know is whether Proxima Centauri b is actually habitable. We've detected the planet through the radial velocity method, measuring the slight wobble of the star caused by the planet's gravity. This tells us the planet's mass and orbit, but not its atmosphere, surface conditions, or whether water exists there. Answering those questions requires more sophisticated observations. We'd need to observe the planet directly, which is extraordinarily difficult because planets are so faint compared to their stars. Or we'd need to observe the planet transiting in front of its star, which would allow us to analyze starlight passing through the planet's atmosphere. Unfortunately, from Earth's perspective, Proxima b doesn't transit. Its orbit is tilted such that it doesn't pass in front of the star as seen from Earth, so we can't use transit observations to study its atmosphere. Direct imaging might be possible with next-generation telescopes. The James Webb Space Telescope, launched in 2021, has the sensitivity to potentially detect planets around nearby stars. But even for James Webb, directly imaging Proxima b would be challenging. Future ground-based telescopes with adaptive optics and coronagraphs, instruments that block the star's light to reveal faint planets nearby, might succeed. Or we might need to wait for a dedicated space-based mission designed to image Earth-like planets around nearby stars. Several such missions have been proposed, but not yet funded. There's another possibility, though. We could send a probe. This is the motivation behind Breakthrough Starshot. A flyby mission to Alpha Centauri could answer many questions about the system. Are there more planets we haven't detected yet? What are the planets' atmospheres like? Is there any sign of chemistry consistent with life? What do the stars look like up close? Even a brief flyby, lasting only a few hours, could return more data about Alpha Centauri than centuries of Earth-based observations. But as we've discussed, Even a flyby probe faces enormous technical challenges. Whether humanity will muster the resources and willpower to attempt such a mission remains to be seen. The cost would be astronomical. Building and launching Breakthrough Starshot, even in its minimal probe form, would likely cost tens of billions of dollars. That's comparable to major science projects like the International Space Station or the James Webb Space Telescope. It would require sustained commitment over decades, consistent funding through changing political administrations, international cooperation among nations that don't always get along. It would require solving numerous technical problems that currently have no clear solutions, and the payoff would be uncertain. The probe might fail during launch. It might fail during acceleration as the lasers push it to 20% of light speed. It might be destroyed by a collision with interstellar dust during the journey. It might malfunction and never send back data. Or it might work perfectly, fly past Alpha Centauri in a few brief hours, capture stunning images and measurements, and revolutionize our understanding of another star system. The risk is high, but the potential reward is extraordinary. Consider what we could learn from a successful mission to Alpha Centauri, even a simple flyby probe. First, we'd get detailed images of the stars themselves. From Earth, even with our best telescopes, Alpha Centauri A and B appear as point sources of light. We can measure their spectra, determining temperature and composition. We can measure their brightness and how it varies over time. But we can't see their surfaces. We can't see sunspots or flares or prominences or any of the detailed structures visible on our own sun. A probe flying through the Alpha Centauri system could image the stars directly, revealing details about their surfaces, their magnetic fields, their stellar activity. We could compare them to our sun, seeing how similar or different they really are. We'd learn more about how sun-like stars behave, which would help us understand our own sun better. Second, we'd search for planets beyond those we've already detected. From Earth, we can only detect planets using indirect methods. The radial velocity method detects planets by measuring the tiny wobble they cause in their star's motion. The transit method detects planets when they pass in front of their star, briefly dimming its light. Both methods work, but they have limitations. They're biased toward detecting large planets close to their stars because those create the most obvious signals. Small planets far from their stars are much harder to detect. A probe in the Alpha Centauri system could search for planets directly, imaging them against the background of space. It might discover additional planets that we've missed. Smaller planets, more distant planets, planets with unusual orbits. Each discovery would add to our understanding of how planetary systems form and evolve. Third, we'd study any planets we find in much greater detail than possible from Earth. If Proxima Centauri b, or any other planet, passes in front of its star from the probe's perspective, we could analyze starlight passing through the planet's atmosphere. Different molecules in the atmosphere absorb light at different wavelengths, creating a unique spectral fingerprint. By analyzing this fingerprint, we can determine the atmosphere's composition. Is there oxygen, which on Earth is produced primarily by life? Is there methane, which can be produced by either biological or geological processes? Are there more exotic molecules that might indicate biological activity? Is there water vapor, suggesting liquid water might exist on the surface? All of these questions could potentially be answered by a close flyby. Fourth, we'd measure the space environment around Alpha Centauri. What's the density of interstellar dust and gas in that region? Are there asteroids or comets, and if so, what are they made of? Is there a stellar wind from the stars, and how strong is it? Are there magnetic fields, and how do they interact with any planets? All of this information would help us understand not just the Alpha Centauri system, but stellar systems in general. Every data point we collect adds to our knowledge, helping us refine our theories and models. Fifth, and perhaps most importantly, we'd be proving that interstellar travel is possible. If a breakthrough Starshot-style probe successfully reaches Alpha Centauri and sends back data, it would demonstrate that humanity can send objects to other star systems. Not easily, not cheaply, but it can be done. That psychological barrier, the sense that the stars are forever out of reach, would be broken. Once we know something is possible, even if difficult, we tend to find ways to improve it. The first computers filled entire rooms and cost millions of dollars. Now we carry more computing power in our pockets. The first airplanes barely flew. Now we cross oceans routinely. The first mission to Alpha Centauri would be difficult and expensive, but it might inspire future missions, better missions, using improved technology. And the scientific value would be immense. Consider the discoveries that could result. If we found definitive evidence of life on Proxima Centauri b or another planet in the system, it would be one of the most important discoveries in human history. It would prove that life isn't unique to Earth, that it can arise wherever conditions are suitable. It would suggest that the universe is full of life, waiting to be discovered. Even if we found no evidence of life, that would also be valuable. It would help us understand the conditions necessary for life to arise. It would refine our estimates of how common life is in the universe. And it would provide a target for future, more detailed missions. If Proxima Centauri b is habitable but lifeless, perhaps we could seed it with Earth life, beginning the process of terraforming another world. That's extraordinarily speculative and raises profound ethical questions, but it's a possibility worth considering. Beyond the scientific value, there's something else important about reaching Alpha Centauri. It represents humanity's first step beyond our solar system, our first physical contact with another star. For our entire history as a species, humans have been confined to Earth. In the last century, we've begun exploring our solar system. We've visited the Moon, sent probes to every planet, landed rovers on Mars, and launched spacecraft beyond the solar system. But we remain bound to our Sun, to this one star out of hundreds of billions. Alpha Centauri represents the next frontier, the first step into the galaxy. If we can reach Alpha Centauri, even with a tiny probe, we've proven that we're not forever confined to one star system. We've shown that humanity is capable of thinking and planning on timescales of decades or centuries, of working together toward distant goals, of overcoming seemingly impossible obstacles. That matters, not just for science, but for our sense of who we are as a species. Are we bound to Earth, destined to live and die on this one small world? Or are we something more? A species capable of reaching beyond our origins to explore the cosmos? Alpha Centauri forces us to confront that question. It's close enough that reaching it seems almost possible, just barely within the realm of achievable technology. Far enough that actually doing it requires solving problems we don't yet know how to solve. It sits at the boundary between the possible and the impossible, challenging us to push further, to achieve more, to think bigger. And that challenge might be the most valuable thing about Alpha Centauri. Not the scientific data we might eventually collect, though that would be extraordinary, but the journey itself, the effort required to reach it. The technologies we'd need to develop, the cooperation required among nations and institutions, the long-term thinking required to plan a mission that won't return data for decades. All of this would change humanity in profound ways. We'd become a species that thinks on longer timescales, that works together toward common goals, that values knowledge and exploration, even when the payoff is distant. These are values worth cultivating. Whether or not we actually reach Alpha Centauri in the near future, the effort to do so would make us better. It would inspire new generations of scientists and engineers. It would drive technological innovation in countless fields. It would remind us that there are still frontiers to explore, still challenges to overcome, still dreams worth pursuing. In that sense, Alpha Centauri is more than just a star system 4.37 light-years away. It's a symbol, a representation of human ambition and curiosity, a reminder that the universe is vast and full of wonders, and that we're capable of reaching toward those wonders even when they seem impossibly distant. And maybe that's enough for now. Maybe the journey toward Alpha Centauri is more important than actually arriving. The technologies developed, the knowledge gained, the inspiration provided. All of these have value even if we never succeed in sending a probe there. But perhaps we will succeed. Perhaps in 50 years or 100 years or 500 years, humans or our descendants or our robotic creations will reach Alpha Centauri. They'll see those 3 stars up close. They'll discover whatever planets exist there. They'll search for signs of life. They'll transmit their findings back to Earth, and we'll receive images and data from another star system for the first time. And in that moment, when we see pictures of alien worlds orbiting alien suns, when we learn what Alpha Centauri is really like, rather than just what we can infer from distant observations, humanity will have crossed a threshold. We'll have become an interstellar species, not in the sense that we've spread throughout the galaxy, but in the sense that we've reached beyond our home star to touch another. We'll have proven that the distances between stars, vast as they are, aren't absolute barriers. They're challenges to be overcome, problems to be solved, obstacles that make the journey difficult but not impossible. And once we've done it once, we can do it again. Alpha Centauri is just the first step. Beyond it lie Barnard's star, Sirius, and thousands of other stars within a few dozen light-years. Beyond those lie the bulk of the Milky Way, hundreds of billions of stars waiting to be explored. The journey is long, the obstacles are immense. But the destination, the knowledge we'd gain, the expansion of human presence into the cosmos, makes the effort worthwhile. Alpha Centauri reminds us that we're small. One species on one planet, orbiting one star in one galaxy among trillions. But it also reminds us that we're capable of greatness, capable of understanding the universe at scales far beyond our everyday experience, capable of planning missions that will take longer than human lifetimes, capable of working together to achieve goals that benefit all of humanity rather than just individuals or nations. These capabilities are what make us special. Not our size, which is tiny, not our strength, which is negligible on cosmic scales, but our minds, our ability to think, to reason, to imagine, to understand, our ability to look at a point of light in the night sky and deduce that it's actually 3 stars orbiting each other 4.37 light-years away. Our ability to detect planets around those stars even though we've never visited them. Our ability to plan missions that might, someday, allow us to actually go there. That's what makes humanity remarkable. And Alpha Centauri, our nearest stellar neighbor, is the perfect target for those abilities. Close enough to study in detail, far enough to challenge us, familiar enough that we can imagine visiting it, alien enough that we don't know what we'll find. It's the perfect first step into the galaxy. Whether that step happens in our lifetimes or in the distant future, whether it succeeds or fails, the attempt itself matters, because it represents hope, hope that we're not confined to Earth forever, hope that humanity has a future among the stars, hope that the universe is full of wonders waiting to be discovered. And sometimes, hope is the most valuable thing we can have. Let's talk about what it would be like to actually visit the Alpha Centauri system, assuming we somehow solved the propulsion problem and could send humans there. The journey would last decades at minimum. Let's assume we achieve 10% of light speed, making the journey about 43.7 years. You'd launch in your 20s and arrive in your 60s if you survived. During the journey, Earth would continue to age at the same rate, But due to time dilation, a consequence of Einstein's special relativity, your experience of time would be slightly different. At 10% of light speed, time dilation effects are small but measurable. Your clock would run about 0.5% slower than clocks on Earth. Over a 43.7-year journey, you'd age about 2.6 months less than people on Earth. Not a huge difference, but noticeable. At 20% of light speed, time dilation becomes more significant. At 50%, it's dramatic. And as you approach the speed of light, time dilation approaches infinity. But we're nowhere near achieving those speeds, so let's stay with 10%. For decades, your home would be a spacecraft, probably relatively small due to mass constraints. You'd live in a confined environment with a small crew, probably fewer than 10 people. Social dynamics would be critical. Psychological screening for crew members would be as important as technical skills. One person having a mental breakdown or a conflict between crew members could jeopardize the entire mission. You'd need robust life support systems capable of recycling air, water, and waste for decades without resupply. Any failure could be fatal. There's no way to get spare parts from Earth. You'd need to manufacture anything you need from materials aboard the ship. Three-dimensional printing and advanced manufacturing techniques would be essential. You'd also need entertainment and mental stimulation. Decades of boredom could be as dangerous as technical failures. You'd probably bring extensive libraries of books, movies, music, games, and educational materials. Virtual reality might help create the illusion of space and variety. Communication with Earth would become increasingly difficult as you traveled farther away. At Alpha Centauri, radio signals would take 4.37 years to reach Earth. A conversation would be impossible. You could send messages, but by the time you received a response, years would have passed. Your mission would need to be largely autonomous. Decisions would have to be made by the crew without input from Earth. This is radically different from current space missions, where mission control on Earth provides constant guidance and support. As you approached Alpha Centauri, you'd begin to see the system in ways impossible from Earth. The two main stars, Alpha Centauri A and B, would separate into distinct objects, no longer appearing as a single point of light. You'd see their orbital dance directly, watching them move relative to each other. Proxima Centauri would gradually brighten from an invisible speck to a visible red star. If planets exist in the system beyond those we've already detected, you'd begin to spot them. Telescopes aboard your ship would be able to image planets directly, measuring their sizes, atmospheres, and surface features. This data would be transmitted back to Earth, taking 4.37 years to arrive. People on Earth would receive images and information from Alpha Centauri for the first time, showing them another star system in detail. The moment of arrival would depend on your mission profile. If you're on a flyby mission like Breakthrough Starshot, you'd pass through the system at high speed, your cameras and instruments working frantically to gather data during the brief hours when you're close enough for detailed observations. Then you'd continue into interstellar space, never to return. Your spacecraft would become an interstellar artifact, traveling forever through the galaxy. If you somehow had the ability to decelerate, you could enter orbit around one of the stars. This would allow extended observations, months or years spent studying the system in detail. You could visit multiple planets if they exist. You could deploy probes to different parts of the system. You could search for signs of life, analyze atmospheres, and study the star's properties up close. Landing on a planet, if one proved suitable, would be the ultimate goal. Imagine stepping out of your spacecraft onto the surface of a world orbiting Alpha Centauri. Above you, two suns might be visible in the sky, Alpha Centauri A and B at different points in their orbit. The landscape would be alien, shaped by different geological processes than Earth. but perhaps still recognizable. Rocks, mountains, valleys, maybe liquid water if you're lucky. The sky would be a different color than Earth's, depending on the atmosphere's composition. The gravity might be slightly higher or lower than Earth's, affecting how you move and how structures stand. Plants, if they exist, would have evolved under different light conditions and might look nothing like Earth plants. The day-night cycle would be unusual due to the binary nature of the stars. Depending on the planet's orbit, you might have periods where both stars are above the horizon, providing bright daylight, followed by periods where only one star is visible, creating dimmer light, and then true night when both stars are below the horizon. Or if the planet orbits close to one star in the pair, the second star might appear as an extremely bright star in the night sky, never providing true darkness. The experience would be simultaneously familiar and alien. Familiar because planets are planets, governed by the same laws of physics and chemistry as Earth. Alien because the specific details, the atmosphere, the geology, the climate, the life, if it exists, would all be different. And all of this assumes we can get there, which brings us back to the fundamental problem. The distances are too large. With current technology, or any plausible near-future technology, sending humans to Alpha Centauri is beyond our capabilities. We can dream about it. We can plan for it. We can imagine what we might find. But actually doing it requires breakthroughs in propulsion, life support, materials science, and numerous other fields that might take centuries to achieve if they're possible at all. Alpha Centauri sits at 4.37 light-years away, close enough to study in detail with telescopes, close enough that we can speculate about visiting it someday, but far enough that it remains, for now, and probably for a very long time, completely unreachable. This is the true scale of Alpha Centauri. It's our nearest neighbor, the closest possible destination beyond the solar system, and yet the journey there represents one of the most profound challenges humanity has ever contemplated. The distances involved aren't just large. They're almost incomprehensibly vast, measured in trillions of miles and years of travel time. They force us to confront the limits of what's possible with technology. They challenge our understanding of exploration and discovery, and they remind us that the universe is far larger and emptier than our everyday experience suggests. When you look up at Alpha Centauri in the night sky, assuming you're far enough south to see it, you're looking at a system we know more about than almost any other star. We know its distance to high precision. We know it's a triple star system. We know it has planets. We know those planets' masses and orbits. We've measured the star's temperatures, compositions, ages, and motions through space. In some ways, we know Alpha Centauri better than we know distant parts of Earth's oceans or interior. And yet, despite all this knowledge, we've never been there. No human has set foot in the Alpha Centauri system. No spacecraft has visited. We've only observed it from a distance, using telescopes to collect photons that have traveled for years across the void. All our knowledge comes from light, from the information carried by electromagnetic radiation emitted by the stars and reflected or blocked by their planets. This is the nature of astronomy. We study the universe by collecting light. We've become extraordinarily good at extracting information from light. We can measure distances, temperatures, compositions, velocities, masses, and even the presence of planets around other stars, all by analyzing light. But there's a fundamental difference between observing something from afar and visiting it, between studying Mars with telescopes and sending rovers to drive across its surface, between detecting exoplanets through tiny wobbles in starlight and landing on an exoplanet to see what it's actually like. Alpha Centauri represents the boundary between what we can observe and what we can reach. It's close enough that we can imagine sending a mission there someday. Close enough that we can discuss specific technical approaches that might work. close enough that the journey time, while measured in decades, is at least comparable to a human lifetime. But it's far enough that we can't actually do it yet. Far enough that every proposed method faces enormous obstacles. Far enough that success would require breakthroughs in multiple fields simultaneously. In this sense, Alpha Centauri is a perfect symbol for humanity's relationship with the cosmos. We can see the stars. We can study them. We can learn about them in extraordinary detail. But we can't touch them. Not yet. Maybe not ever. The universe has given us the ability to observe and understand, but it has also imposed a fundamental barrier, the speed of light limit, the vast distances between stars, the enormous energy requirements for interstellar travel. These aren't just technical challenges. They're features of how the universe is structured. They might be limitations we can never fully overcome. Or perhaps, in the far future, humanity will develop technologies we can't currently imagine. Perhaps we'll discover new physics that allows faster-than-light travel or teleportation or other methods of crossing interstellar distances that seem impossible today. Perhaps artificial intelligence and robotics will advance to the point where we don't need to send biological humans. We could send machine intelligences capable of functioning for centuries, unaffected by the long journey times. Perhaps we'll develop technologies to upload human consciousness into machines, making us effectively immortal and capable of surviving indefinite journeys. These ideas are speculative, bordering on science fiction, but so was everything about space travel a few centuries ago. The Apollo moon landings would have seemed like fantasy to someone in the year 1700. The James Webb Space Telescope observing galaxies billions of light-years away would have been inconceivable. We've achieved things that once seemed impossible. Perhaps interstellar travel will join that list someday. But for now, Alpha Centauri remains tantalizingly out of reach. A goal we can see but not touch. A destination we can dream about but not visit. The first star beyond our sun, so close in cosmic terms, and yet separated from us by a gulf so vast that crossing it might require fundamentally rethinking what we mean by travel and exploration. This is the reality of living in a universe where stars are separated by light years, where the cosmic speed limit is enforced absolutely, where the vast majority of space is empty void. Our sun sits in a tiny bubble of warmth and light, surrounded by planets and smaller bodies, all held together by gravity. Beyond the edge of that bubble, beyond the Oort cloud at about 2 light-years from the sun, space becomes truly interstellar. The sun's influence fades to near nothing. Alpha Centauri's influence begins to dominate. And in between, there's nothing. Just empty space. Cold, dark, silent, and almost entirely devoid of matter. This emptiness extends in all directions, between every star and its neighbors, between galaxies, between galaxy clusters. The universe is mostly empty, with tiny islands of matter scattered throughout, and those islands are so far apart that reaching from one to another represents a fundamental challenge. We've explored our own island thoroughly. We've sent spacecraft to every planet in our solar system. We've landed on the Moon, Mars, Venus, Titan, comets, and asteroids. We've sent probes to the edge of the heliosphere and beyond. Voyager 1 and Voyager 2 have entered interstellar space, leaving behind the sun's bubble and traveling into the void between stars. But even these most distant human-made objects, traveling for nearly 50 years, are still only about 0.06% of the way to Alpha Centauri. They've barely left our island. The journey to the next island has only just begun, and it will take tens of thousands of years to complete at their current speeds. This is where we are, inhabitants of a small rocky planet orbiting an average star in a typical region of a spiral galaxy. We've learned to study the universe around us in extraordinary detail. We've mapped billions of galaxies. We've detected thousands of planets around other stars. We've measured the universe's age, size, expansion rate, and composition. We've traced the history of the cosmos back to fractions of a second after the Big Bang. Our knowledge is vast, but our reach is tiny. We can observe across billions of light years, but we can barely reach 4 light years. We can see distant galaxies as they were billions of years ago, but we can't visit the nearest star. This asymmetry between observation and exploration is one of the defining features of modern astronomy. We've become a species that can see almost everything but touch almost nothing, and Alpha Centauri sits right at that boundary. Close enough to observe in detail, far enough to be unreachable. A reminder of both how much we've learned and how limited we remain. The true scale of Alpha Centauri isn't just about the numbers: 4.37 light years, 25.69 trillion miles, 43.7 years, at 10% of light speed. These numbers are important, but they don't fully capture what it means. The true scale is about the relationship between human ambitions and cosmic reality. We want to explore. We want to visit other worlds. We want to know if life exists beyond Earth. We want to see other stars up close, to walk on other planets, to make contact with other civilizations if they exist. These are natural human desires, extensions of the same curiosity that led our ancestors to explore Earth, crossing oceans and continents, to see what lay beyond the horizon. But the cosmos presents a horizon that might be fundamentally uncrossable, not because we lack the courage or determination, but because the distances are simply too large given the constraints of physics. This is humbling. It forces us to recognize that our species, for all our achievements, remains bound to a tiny corner of the universe. We can observe the wider cosmos, but we might never travel far beyond our solar system. We might be eternal watchers, never participants. Or perhaps this limitation is temporary. Perhaps future generations will look back at our era and marvel at how we thought interstellar travel was so difficult. Perhaps they'll visit Alpha Centauri routinely, the way we now fly between continents. Perhaps the barriers that seem insurmountable to us will be overcome through technologies we haven't yet imagined. We can't know for certain. What we can say is that Alpha Centauri, our nearest stellar neighbor, remains profoundly distant. It represents the first step beyond our solar system, and that step is so large that it might take centuries or longer to achieve. Every time you see Alpha Centauri in the night sky, you're looking at the closest star beyond our sun. You're seeing 2 sun-like stars and a small red dwarf, gravitationally bound together, orbiting their common center of mass. You're seeing a system that has planets, including at least one in the habitable zone. You're seeing a destination that humanity might someday reach. But you're also seeing a reminder of just how vast the universe is, how empty space is between the stars, how challenging it would be to cross even this shortest of interstellar distances. The light you see left Alpha Centauri 4.37 years ago. It's been traveling through space at 186,000 miles per second ever since, never slowing, never stopping, crossing the incomprehensible distance between their system and ours. And when that light enters your eye tonight, it completes a journey that took longer than most undergraduate degrees. That light carries information about what Alpha Centauri looked like years ago. If something dramatic happened there, an enormous flare from Proxima, a collision between planets, a signal from an alien civilization, we wouldn't know for over 4 years. And if we sent a response, it would take another 4 years to arrive. The universe enforces patience. It enforces humility. It shows us wonders and then places them just barely out of reach. Alpha Centauri is right next door, our closest possible destination, a system we can see clearly and study in detail. And yet, it might as well be on the other side of the universe, for all our current ability to visit it. This is the true scale of Alpha Centauri, and by extension, the true scale of the cosmos we inhabit. A universe of vast distances, tiny islands of matter separated by incomprehensible voids, a place where light takes years to cross the shortest gaps between stars, where any journey between stars would outlast most human lifetimes, where the night sky shows us thousands of destinations we might never reach. We are, for now, bound to our solar system. Perhaps that will change someday. Perhaps humans or our machine descendants will cross the void and explore the galaxy. Perhaps we'll find ways around the barriers that currently seem absolute, but for now, Alpha Centauri remains what it has always been, our nearest neighbor, a triple star system, 4.37 light-years away. Close enough to see, far enough to be unreachable, a symbol of both the vastness of the universe and the limits of human reach. And when you understand the true scale of just this one system, the nearest star beyond our sun, you begin to grasp something profound about the universe we live in. It's larger than we can truly comprehend, emptier than we naturally imagine, and more challenging to explore than almost anything we've ever attempted as a species. But it's also beautiful. The fact that Alpha Centauri exists at all, that three stars can be bound together by gravity for billions of years, that planets can form around those stars, that we can observe and study them from 4.37 light-years away. All of this is extraordinary. The universe is structured in a way that allows complexity to emerge. Atoms form from the debris of dying stars. Atoms combine into molecules. Molecules form planets. Planets orbit stars. Stars gather into galaxies. And occasionally, on at least one planet that we know of, atoms organize themselves into living things capable of looking up at the stars and wondering what's out there. That's us. We're the universe's way of knowing itself. Stardust that has become conscious, capable of understanding its own origins and contemplating its place in the cosmos. Alpha Centauri represents both the vastness of the universe and the remarkable fact that we can understand it. 4.37 light-years is an incomprehensible distance by human standards. We can't cross it with current technology. We might never be able to cross it, but we can observe it, we can measure it, we can understand it. We know what Alpha Centauri is made of, how old it is, how fast it's moving, whether it has planets. We've learned all of this without ever leaving Earth, using nothing but telescopes, mathematics, and careful observations. That's an incredible achievement. It means that even if we can never physically visit Alpha Centauri, we can still know it. We can understand our nearest neighbor in ways that would have seemed like magic to our ancestors. And that understanding connects us to the cosmos in a profound way. We're not separate from the universe. We're part of it. Made of the same atoms, governed by the same physical laws, subject to the same forces. Alpha, Centauri, and Earth are siblings in a sense, both born from clouds of gas and dust, billions of years ago, both evolving according to the same principles. The main difference is distance. We happened to form here. Alpha Centauri happened to form there. And the space between us, while vast, doesn't change the fundamental connection. We're all part of the same universe, the same cosmic story that began 13.8 billion years ago with the Big Bang and continues today. Alpha Centauri is part of our story, just as we're part of the galaxy's story. And someday, if we're lucky and persistent and clever, we might add a new chapter to that story, the chapter where humanity reached beyond its home star to touch another, where we crossed 4.37 light-years of empty space to explore a new system, where we proved that the distances between stars while vast, aren't absolute barriers. That chapter hasn't been written yet. It might not be written for centuries. It might never be written, but the possibility exists. And as long as that possibility exists, as long as humans look up at the night sky and wonder what's out there, Alpha Centauri will remain important. Not just as a star system, but as a goal, a destination, a challenge, a reminder of both our limitations and our potential. The journey to Alpha Centauri, if it ever happens, will be one of humanity's greatest achievements. A testament to our ingenuity, determination, and willingness to push beyond every boundary. But even if we achieve it, even if we somehow build spacecraft capable of crossing those 4.37 light-years, it will only be the beginning. Beyond Alpha Centauri lie billions of other stars, most far more distant, scattered throughout a galaxy 100,000 light-years across. And beyond our galaxy lie trillions of other galaxies, stretching across an observable universe, 93 billion light-years in diameter. Alpha Centauri is step one, and step one might take us centuries to achieve. The scale is staggering. The distances are immense. The challenges are profound, and yet, knowing all this, we still look up, we still wonder, we still dream of the day when humanity might reach beyond our solar system and touch another star. That's what Alpha Centauri represents. Not just a destination, but a challenge. A question posed by the universe itself. Can you cross this distance? Can you reach beyond your tiny island to touch another? For now, the answer is no, but someday, perhaps, the answer will change. And on that day, when the first human spacecraft arrives at Alpha Centauri after decades of travel, when cameras and instruments capture images of alien worlds up close, when we finally bridge the gap between our star and the next, it will be one of the defining moments in human history. A moment when we stopped being a species bound to one star and became, truly, a spacefaring civilization. That moment may be centuries away. It may never come, but the possibility exists. And that possibility, remote as it might be, is what makes Alpha Centauri so significant. It's not just the nearest star, it's the gateway to everything beyond, the first destination on a journey that could, someday, take us anywhere. Thanks for staying with me through this exploration of distance, scale, and the profound challenges of interstellar travel. Alpha Centauri is 4.37 light-years away, right next door in cosmic terms, and yet so distant that reaching it represents one of the greatest challenges our species has ever faced. When you look up and see that bright star in the southern sky, if you're fortunate enough to be far enough south to see it, remember what it represents. Not just three stars orbiting each other, but a destination that reveals the true scale of the universe we inhabit. A reminder that space is vast, distances are enormous, and yet we're capable of understanding and maybe, someday, overcoming those obstacles. Alpha Centauri is waiting, 4.37 light-years away. The nearest star beyond our sun, our first step into the galaxy.